Good afternoon, this is Schweitzer, and this is a little video on how to write, let's call it solubility reactions, or we call it a precipitation reaction. Now, this is going to be slightly different than what we've seen with KSP, although it is in fact the same thing. I'll show the difference between how they standard write it. If we were to take a solution, let's say, of AgNO3 aqueous, and we're going to add this thing to a solution, let's say, of NaCl, alright, we're going to get a beaker. Let's draw these beakers out ahead of time here. And we get this guy, which is going to be Ag plus ions and the nitrate ions in a 1-to-1 ratio. And then here we're going to get a beaker with the Na plus ions and the Cl minus ions. We dump them together, and you should be aware that different combinations of different ions have different solubilities. That's shown in a KSP. The KSP of a certain, let's say, AgCl is 3e to the negative 7th. Whereas a different combination of Ag and a different anion will be different. So when we dump these together, the silver and chloride now being present in the same beaker, even though it's in a larger volume, I'll draw a bigger beaker to show more volume. It's less concentrated, but the AgCl is going to form precipitate on the bottom, and the Na plus and Cl NO3 minus stay in solution. So I only drawn one formula unit of it, but that's what goes on here. Now, in this case, the way I would write this is it'd be AgCl plus NaNO3. Okay, so in some sense we do KSP, but we do KSP with only things that are ever so slightly soluble, and we're talking just really microscopically soluble. So on a bigger picture, we would note that silver chloride would generally thought to be insoluble, and this is AQ aqueous. As far as the AP exam is concerned, you don't really need to memorize any solubility rules. The only solubility rules we really look for in honors chemistry in this class would be when you have a cation and you have an anion, if you have a cation that is sodium, a cation that's potassium, a cation that's ammonium, or an anion that is nitrate, these guys are just extremely soluble. Regardless of what we have as an anion, or a cation, this is what I refer to in honors chemistry as a quick check. Just, we know that these things are always very, very, very soluble, and if they're saying something's going to precipitate, then we know this is not going to precipitate. So by process of elimination, we might be able to figure a thing or two out. All right, so you would not be required to know necessarily that the silver and chlorine forms a solid. They may indicate that to you in some way. Alright, so this is the way we wrote this equation. I might even rewrite it down below so it can stay in the field of view. Alright, this form is referred to as, okay, we're describing what's in these beakers here, before beakers, after beaker, is as the molecular equation. It's going to be AgNO3 plus NaCl goes to AgCl solid, I'll put a solid just because I can, plus NaNO3. Whether you choose to put aqueous on the other guys is up to you. Now, this is showing them as if they're actually together. as if they're molecules, hence the word molecular equation. Probably the most common way which we write things, even though it's probably not the most correct way to write things. The newer, a different version, less common in fact, is called the ionic equation. And this shows each thing as they truly are in solution. The silver nitrite is in fact separate, so we'll go Ag plus NO3 minus plus Na plus Cl minus. These are all my reactants. Notice they're all separated because they're not even together in solution. Okay, and in the end I have an AgCl solids actually together plus a Na plus NO3 negative. These guys stayed separate, so we kept them separate. Alright, the last one we're looking at here is called a net ionic equation. And this is one where we remove spectators. Okay? Spectator is anything that it goes unchanged from start to finish, not changing. Okay? Now, in this case, what's not changing? The nitrate staying floating around, the sodium, these guys are floating around before, they're floating around after, so therefore we remove them. We have Ag plus Cl minus yields AgCl. This is your standard precipitation net ionic equation. This is very popular, and this one's very popular. Very often they'll ask for answers to be in net ionic. Alright, so this is the reaction we use for this type of it's pretty typical. But for KSP, for some reason, and it's not better or worse, we always just write out the other way around. AgCl comes from Ag plus Cl negative. This is just a standard way that we do this. Solid is on the left side, a reactant. The aqueous is the product. Why? Well, when we write out our KSP, then it would be the concentration of the Ag plus ions times the concentration of the chloride ions over 1. Technically, if I wrote it this way, then it would be the KSP equals 1 over the concentration of Ag plus and Cl minus. Now, there's nothing wrong with this, okay, and there's nothing wrong with that. It's just that everybody else is doing it like this. So for continuity, and that everyone is comparing the solubilities and doing KSP the same, we always do it like this, solid on the left. Just an FYI. This video is more about doing the molecular equation, the ionic equation, and the net ionic for typical things of reactions. So let's try. I'm going to throw out two more examples here, and you can pause the video if you would like to try this on your own, and then from that point you should be okay. Let's take, for example, let's go something that would precipitate Pb parentheses NO3 2 plus Na, let's go CO3 and 2. Okay, so the first thing you do for a lower, anybody really would be, okay, I want to know what my possible combinations are located. Okay, so I'm going to do, well, you can pause. If you know at this point what you're doing, you can pause the video now and you can run it on yourself. I'm looking for the molecular equation, I'm looking for the ionic, and the net ionic. So if you can do it at that point, then you could be just fine. Otherwise, I can explain a few things here, and then from there, you can run these things through. So either way, at some point, you might want to say, okay, well, this is a -1, this is a +2, this is a +1 and a -2, and as I put them into the new beaker, then at this point the lead would have opportunity to precipitate with the carbonate, and the sodium would have an opportunity to precipitate with the nitrate. So my possible combinations, my possible precipitations would be either NaNO3 or PbCO3. This is a +1, this is a -1, +2, -2, so they're written correctly. Notice that the charges do not change throughout this reaction from start to finish. That's because it is not an oxidation reduction reaction. Okay, next thing, I did note to you that sodiums and nitrates always produce aqueous processes, or ions, or products. So this is an aqueous, and this would be a solid. Take a moment now at this point and write out the molecular, the ionic, and ionic. Alright, so this is the molecular. The ionic would be Pb +2 plus NO3 -2 -1 plus Na plus CO3 -2 goes to Na plus NO3 minus plus PbCO3. And I would keep this as a together as a solid. All right, the net ionic would be, again, removing things that don't change. That would be the sodium nitrate, so Pb, and then 2 plus CO3 -2 goes to PbCO3. And you should be able to draw a picture of before and after of what beakers would look like. All right. Next up, we got. Let's try another example here. Let's go with calcium nitrate plus potassium oxalate. All right. Take a moment, write out the products. You can balance it if needed, and then this will be the molecular version. And then I want you to write the ionic, and then the net ionic. Okay, so here's the answer. This is a +2 -1, +1 -1. Swap cations and anions, or swap cations, I guess. So the calcium have opportunity to produce here calcium oxalate and potassium nitrate. In this case, we have all balanced. Nothing here that would need balancing. +2 -2, so charge balance, we're all set. Ionic would be calcium +2 plus NO3 -1 plus potassium +1 plus C2O4 -2 yields calcium oxalate plus potassium plus NO3 minus. Net would be calcium 2 plus C2O4 -2 goes to calcium oxalate. And that's pretty much it. So that's what we got for this. Thank you very much.